the key thing, I think, for situations where you want to be using mathematical optimization is that there's some kind of outcome that you're trying to maximize or minimize. And I
Hmm.
guess that is also something that's different about when you think about, you made the distinction at the outset between making predictions, like predicting the future, versus being prescriptive.
Hmm.
And with something that's prescriptive like this, you're not taking necessarily a bunch of historical data and just trying to say, oh, if my inputs happen to be these inputs, what am I going to get? What you're doing with this kind of prescriptive approach, with this mathematical optimization that Gurobi offers, is that you are saying, how can I maximize, given these constraints,
Hmm.
how can I maximize some outcome or minimize some outcome? So, how can I maximize profits or how can I minimize delivery time? And then, as you mentioned there, what you call the secret sauce, the key thing that Gurobi is offering is that, I guess, kind of figuring out what your full optimization space is. That can be hard, but it's not the hardest thing.
Hmm.
The hardest thing is then being able to explore over that space, which, as you mentioned, in the real world, it could be millions of possible decision points that could be binary or
Hmm.
continuous. And so the key, the secret sauce is this Gurobi solver that can then, in a lot of situations, work extremely rapidly at optimally solving, provably optimally, if I remember
Exactly.
correctly, that
That
it's
is
not,
it.
this isn't an approximation of what the maximum
Hmm.
profit would be or the minimum delivery time. It's like, it's mathematically proven to be the maximum or the minimum,
Hmm.
whatever you're looking for, and it typically happens rapidly. At least in my hands-on experiences with it, and critically, it's easy to access through, say, Python.
Hmm.
So you've provided lots of, and we'll provide links in the show notes to lots of Jupyter notebooks and tutorials that you've created to allow people to be accessing the Gurobi optimizer through Python code.
Exactly. Yeah, and the what you're saying about how the constraint part of it is a huge thing, and makes things very very difficult. And again, like the this requirement for binary decision variables, for integer decision variables, like making if you're building cars, you can't build half of a car, so it may be very very important that you're deciding things in integer quantities. So yeah, those are a couple of the key things that sort of differentiate mathematical optimization from something that you would do purely like calculus based. And you have like, oh, I have some curve and I want to find the maximum or minimum of it. So why don't I just take a couple of derivatives and bada bing bada boom, I'm done. Stuff like that. While those methods sort of are incorporated in some things, but it differentiates from that because of all of those restrictions and the constraints and the ideas that well, if I'm a binary decision variable, something like yes, no, do I want to open a warehouse in the city? Well, if I you can then have like if thens, like if I open a warehouse in this city, then I shouldn't open another warehouse within 200 miles, because why would I do
Right,
that? So then you can
right.
build that logic into the model and say and then say, okay, well, if I build any location, I build a warehouse, or any location that I put a burrito truck, I do not want to put another warehouse or whatever truck within a certain distance, because it just doesn't make sense, or because of any other business reasons that you may have, that you may know of yourself, or people may be sort of telling you this is the way we need to do things. Then you just it's yeah, mathematical optimization is really just about modeling logic via algebra. That's sort of where the art of it more or less rests, is being able to take those business problems that people are just verbally telling you, and then you say, okay, I understand what you're saying, and then you translate it into some algebra, and then you translate that algebra into code. And Python is by and large our most popular API, and it's really really good. Not just saying that as an employee, but as someone who used it before joining, and everything. That it is great. And it just makes everything, just makes that whole process pretty seamless. And yeah, that's why mathematical optimization as a whole, I think, is it's different from machine learning because of that. It you Modeling business logic is not something that machine learning does. If your data does not contain these cases that have happened, then you're sort of blind, first off. And even if it does, what the outcomes were, what the decisions were, all the other things that can influence like such a regression, let's say, like how do you know that things were being, it's just relying purely on past data is not the approach, because what if the past was, things have changed, there's underlying just so many underlying things that have changed, particularly, if you think of, you know pre-COVID, during COVID, post-COVID type of things. um, uh, Events like that just sort of destroy predictive models, because how can you predict what's going to happen during a once in a generation sort of outbreak, when it's once in a generation? How much data do you have on that? But something like mathematical optimization, when you're describing the logic of a system, sort of like a supply chain network or a schedule, or how I want to invest in a portfolio of stocks or something like that, like that logic stays the same, independent among, even, you may want to say, okay, we're in a pandemic now, I want to be more conservative. Well, you can then sort of, I want to be more conservative with how I invest or something like that. Then you can really model that with logic, and you can, as opposed to relying on underlying data to make some decisions about that. That's also not to say that these two things shouldn't work together. They definitely do.